Okay, well, looks like we're back online. So, are there any questions? So, let me recall where we were on this representations of R. So, we have defined the Hamilton quaternions. This is an algebra over R. And with this basis and these relations, and then we looked at the units so the elements of norm 1, norm, if we write it in this way with UIs real numbers, then the conjugate is you change sign to all the coordinates other than the real one, and u times u bar, you can check that it's the sum of the squares. Another way, so the way we gave this was thinking of the complex numbers inside H by sending I to I, so the I of the complex numbers sending to I, 1 to 1. J then satisfies that JA is J in bar, or the, let's see what notation I'm going to use. I think I want to, yeah, so it's okay. So if we have something of the form A, B, J, our quaternion, where A and B are complex numbers, then U conjugate is A conjugate minus B conjugate J. So in this notation, A would be U0 plus U1I, B is U2 plus U3J, 3I. And then we have a map from H to the matrices. So, in fact, the embedding, which in this notation ABJ maps to A. What was it? AB minus B bar, A bar, right? So, I mean, there's a few things I'm saying without proving, or I think some of them we did last time, but they're fairly simple. So, this is a algebra homomorphism. So it's additive, which is clear, and then but it's also multiplicative. So if we look at elements that are invertible, it will map to GL2. So invertible matrices, and inside here they are the invertible elements of norm 1, and this maps to SU2. So in fact, this gives us isomorphism. Okay? And what we argued was that if you had a finite group, so G inside H1 is finite, and then by mapping, so G is sitting inside H1, which maps to SU2, is isomorphic to SU2, which sits inside GL2. So this gives a two-dimensional representation of G. And what we argued is that if G is non-abelian, let's call this representation rho, then rho is not real. So real, recall that means rho is real if rho arises from is isomorphic. So if you can change basis so that the map actually maps to GL of B0, where B0 is a vector space over R. So concretely it means that you can change basis so that the matrices that represent G, so via rho, have all real entries. And so an example of such a G is the quaternion group. I think normally you write it as Q8. It's simply the group consisting of plus or minus the basis vectors. So this is a group of order 8. Called the quaternion group. It's not abelian. Ij is minus Ji. So it's an example of a non-abelian finite group of SU2 via this isomorphism with the quaternions. I think in physics the matrices you get are called Pauli matrices, I think. They come up in physics. Pauli matrices. I'm not sure how to do that. Oh, we can turn it off from here. Noisy. Okay, so this thing more or less we already mentioned. Maybe we also mentioned, or I think we also discussed, but let's say again, what's the character table? Of Q8. So Q8 the center of Q8 consists of plus or minus 1, the things I commute with everybody. So that's a normal subgroup. And if you divide by this normal subgroup, you get a group of order 4, where plus or minus 1 are both because you put them in the quotient. So now Ij is the same as Ji in the quotient, so this group is isomorphic to the cyclic group of order 2 cross the cyclic group of order 2. Because you now, by most quotient out by plus or minus 1, you forget the signs. And so, so this is a group of order 4, which is abelian. They all are. And therefore, this quotient group has 4 one-dimensional representations. So Q8 maps surjectively to C2 plus C2, and there are 4 one-dimensional representations. And so I think I'll just leave it to you to check that in fact there are 4 forget to, this should be 5 actually, conjugacy classes. 1 and minus 1 in the center, their own conjugacy class. Then I and minus I are conjugate, J and minus J are conjugate, and K and minus K are conjugate. To get from I to minus I, you conjugate by J and so on. And you cannot move from I to J by conjugation. So there should be 5 representations, irreducible representations, and there we have 4. So we have certainly the trivial one, and then the 4 representations that come from this quotient. In the quotient, the minus 1 goes to 1, so there's always going to be these values. And then we have the all possible ways to have minus 1s in. So these are all the one-dimensional representations of the quaternion group, and there's 5 conjugacy classes, so there should be 5 irreducible representations. And in fact, the one that is missing is exactly the one that comes from this embedding into SU2. So recall that if you have a map to SU2, then the traces are all real, because the traces of matrices in SU2 are real. So this will have real values. And maybe we should do this. So let's compute rho of minus 1 and the other ones with. So minus 1, so let's see what rho does. Minus 1, the quaternion minus 1 goes to the matrix minus 1, minus 1. Let's write minus 1 goes to, it's an algebra isomorphism, so minus 1 has to go to minus 1. I, J, K, where do they map to? So these are these Pauli matrices I was talking about. So where does I go to? So we have the expression for any A, B, J, yeah? So what is it? So this is just I plus 0 of J, so B is 0. So it's A, which is I, B is 0, and then minus conjugate. Sorry, so it should be 0 minus I. J, on the other hand, goes to where? A is 0, yeah, and B is 1. So minus 1, 0. And K is I times J. So to multiply this is K is equal to I times J. So that means that A is 0 and B is I. So we get 0, 0, I, and should be I. Yeah? And these will be, if you check that these are matrices of determinant 1 and matrices in SU2. So this is how the map row, what row does to our elements. And notice that in all cases the trace, well, this is minus 2, 0, 0, 0 for all the I and the J and the K. The trace is 0, so the character is minus 2, 0, 0, 0. Okay. So the character values are real because the traces are, the matrices are in SU2 and the traces are always real. But this representation cannot be realized in R2. So you cannot change bases in such a way that all of these matrices become real. This action, a two-dimensional action of this group, has to happen over the complex numbers. Okay, so what we're trying to do is determine when, if we have a representation, when will it be possible to realize it over the reals, and when will it not? So this is an example where it's not, and how can we tell? How could we could have told that that was the case from the beginning? Let me make another comment while we're at it. This is a group of order 8. What other groups of order 8 do you know? Hmm?
We have the symmetry of a square.
The symmetry of a square.
We have also the 4.
All the abelian ones. So let's just keep the just consider the dihedral. Yeah. So let's look at the so this is a parentheses. Let's look at this group. So these are symmetries of the square. And this therefore acts on 4 space by moving the square around. So this is a two-dimensional representation, which is real. It's by its very construction acting on R2. So this is a two-dimensional representation, which is real. In fact, it is a irreducible representation because there is no line that is fixed by the group. So what I'd like to do now is compute this whole character table. And we'll discover that the character table looks exactly like this one. Okay, so I can erase this top here and give names C1, C2, C3, C5, and you wouldn't be able to tell if I wrote the character table of D4 or of Q8. So it's just a fact of nature that you can have groups that are not isomorphic that have exactly the same character table. So character table doesn't tell you what the group is. Somehow you're not going to be able to reconstruct what the operation of multiplication is on the group from the values of the character. In particular, this row here for this group corresponds to a representation that is not real, and for D4 it will correspond to a representation that is real. So you need more than just the character values in order to determine if the representation is real or not. So I'll just going to go over this somewhat quickly and give you a few hints of how you do this. Maybe could be one of the homework problems. You haven't received any homework problem, have you? Or, yes, you have? Okay. So I don't know if Victoria included this, but I'll send you. I think it's something that was worth going over. So let me do this in general. They give a group of order 2n, D2n. You can give it in terms of generators and relations as generated by two elements.
Sorry, above you are using the rotation dn.
I don't know. It has order 2n. There's an ambiguity. Some people use dn and some people use d. So I here use d4. I use both notations at the same time. So maybe thank you. So these generators satisfy the relation that if you conjugate tau by sigma, then you get tau inverse. And tau, so this is a symmetries of a regular n-gon, and tau corresponds to a rotation of angle 2 pi over n, for example, counterclockwise, and sigma corresponds to some reflection, let's say, with respect to one of the axes. And to you can find the character table of this group, and you can do this the same way we did S3. In fact, S3 is isomorphic to D3, and the same way that we analyze all representation of S3 by hand, you can use the same idea for dn. So I want to keep the table, but so for D4 we'll have the same table with different labels for the conjugacy classes. So just to sketch, so for dn, so let's say V is the representation of dn, then restrict to the action of just the group generated by the rotations, what you'll find, so V will decompose into eigenspaces where they're indexed by the nth root of unity. Sigma of V, sigma will have to be V sigma inverse. And so there's going to be two situations depending on whether n is even or odd. If n is odd, the only of these two pieces that are going to be fixed by sigma is when theta is equal to 1. And in that case, so if n is odd, you'll have V is V1 direct sum, all the other pieces where theta is not 1. B1, these are going to come in pairs, V sigma and V sigma inverse, and sigma, V theta and V theta inverse, and sigma will move one to the other. They are going to form a two-dimensional representation. a sum of two-dimensional representations corresponding to this row, and this one will break into two pieces corresponding to plus or minus 1. And if n is even, you'll have v is v1, and then there's also v minus 1, which now is among the numbers whose nth root is n power is 1, and then the rest and then you'll have two parts that are sigma decomposes this one into two pieces and this one into two pieces, and that's where in the case of 4, for example, you'll have these 4.
I'm just confused. Why sigma maps?
You just do the calculation, it comes from this.
Okay.
You just see this is an eigenspace for tau, and if you just look at this relation, sigma will have to take an eigenspace, an eigenvector with zeta to an eigenvector with zeta inverse, just like we did for ST. Okay, so this is just a bit quick, but I wanted just to sketch how you go about it, and then this will allow you to find all the irreducible representations of theta-hero group. And of course, there's one that is visible here, which is the action on R2 that preserves the n-gon, and that's going to be one irreducible representation. And then there'll be others that come from this V1 or V1, V minus 1. So for D4 we have this. The conjugacy classes for D4, you can index them. Well, there are going to be 5. I think I'll just leave it like this. So for D4, you're going to have the same character table. As Q8. So what changes is how the multiplication in the group moves these columns around. The columns are the same, but the operation in the group will do something different to the conjugacy classes. Okay, so I'll write out as a homework problem a little bit more carefully what you're supposed to do. Okay. So now our task is to somehow figure out when could we have, if we have a representation, when can we be sure that it comes from an action over R, and when can it not? So the question then is, when is V real? So V is a representation a priori over the complex numbers, and then we want to determine when it comes from something defined over the real numbers. So the very least thing that should happen is that the character values must be all real numbers, because if the matrices are going to be represented by real matrices, then the traces are real. So this is certainly necessary, and the standard notation is that if you have a representation which does not satisfy this, so some of the traces are complex, then the representation is called complex. Although it's a bit ambiguous because a priori they're all complex, but some cannot be reduced to R, and those are called complex representations. Okay, now to be real is to say that you're equal to your conjugate. So statement is this. Now on the other hand, the character, the conjugate of the character is the character of the dual representation. So to say that your character values are real is the same as saying that the character of the representation n is the same as the character of its dual. Now, if two characters are the same, then the representations are isomorphic. So all of these are equivalent notions. V is isomorphic to V dual as a representation.
Did you just mention before that Q8 and D4 has the same character table, but there are no isomorphic groups?
Yep.
And the representation that I isomorphic?
No, I mean they're different groups, right? They have the same traces. So here what we're saying is we have one group and two characters of the group that have the same values. Then the representations of that group are isomorphic. If you have two groups, different groups, then the characters are, typically there's no way to compare one with the other. There will be more conjugacy classes in one group than another, and so on. Okay, now, so let's follow this line of reasoning. V is isomorphic to V dual as G representations. It means that there is a map, phi, that goes from V to V dual, which is an isomorphism of vector spaces, which is also G linear. So it preserves the action of the group. Okay? Now, whenever you have a map, whenever you have or you chose a map from V to V dual, an isomorphism, as vector spaces, these vector spaces are isomorphic always, but in a non-canonical way.
You get a bilinear form?
Yeah, so with such an isomorphism, you get a bilinear form, and conversely. So, continuing with this line of all of these being equivalences, what we have is V, it goes from V to V, which is bilinear, non-degenerate, and we can define it as follows. We have two vectors, u and v. Then you can define this as phi of u evaluated in v. Yeah? Phi of u is some linear form, some element of v dual. That linear form can then be evaluated on the vector v. And if you follow the properties of all these maps, you'll see that this is a bilinear map. And conversely, we have a bilinear map that is non-degenerate, then it gives rise to an isomorphism between V and V dual. And because everything we're doing is G linear, this is all, everything here is G linear. Now this is a bilinear map, not necessarily a Hermitian map. We have this, nothing here has involved how complex conjugation comes into this picture. Now, if V is irreducible, then what can we say about the situation? What if I have two such maps? What can we say about them?
We can use Schur lemma.
Yeah.
So the i's are isomorphic or
What is it?
Well, if we have two of these maps, that isomorphisms between V and V dual, Phi1 and Phi2, you can take Phi1 and then compose with Phi2 inverse, and this would be a map from V to V, which is an isomorphism and also G-linear, and therefore by Schur's lemma it has to be a scalar. Yeah, in fact a non-zero scalar. Which is to say that Phi1 is equal to lambda Phi2, for lambda some non-zero scalar. Or just to say it in words, I can just say that if V is irreducible, then Phi is unique up to scale. Yeah. And the same goes for B, because this construction between B and Phi is sort of natural one-to-one. So I can just say the same thing, that if we now pose ourselves in the situation of B having real valued characters and irreducible, then it has a G invariant bilinear map, which is unique up to scalars. So let me summarize then that V, real valued character, irreducible, then there is a bilinear map from B to V to C, which is non-degenerate, G is stable, G invariant, and unique up to scale. Now, a bilinear form is the same as giving a linear map from V dual tensor V dual to C. No, let me say it's the same. So this gives an element in V dual tensor V dual. Right, so B, if we pick a basis V1 to be n basis of V, V1 dual, Vn dual, and dual basis, then B of Bi Bj is some number Bij. So if I want to compute the value on a pair U and V, this is the same as computing Bi dual so B is the same as this. Let me put it this way. So this pair Bi dual tensor Vj dual out of a vector, a pair of vectors, picks out the ith coordinate of the first vector and the jth coordinate of the second vector. And then, because it's bilinear, if you know the value on those coordinates, you know the whole bilinear form. So, to give a bilinear form is the same as just giving a vector in this tensor product. Now, as we discussed before, if we take the tensor product of a vector space with itself, this is a G representation, and as G representations, it breaks up into two pieces, the sim2 and the wedge2. And if we have some bilinear form corresponding to, so think of bilinear forms as elements in here, then this decomposition is not other than saying that B breaks up into a sum of a symmetric bilinear form and an alternating bilinear form. So, and that's, if you want to think of this concretely, this is simply saying that you can write a bilinear form as a symmetric thing plus a skew-symmetric thing. Yeah. Now, the point is that if B is unique up to scalars, so if you decompose it in this form, each one of these is, because these are G representations, each one of these is G invariant. Okay, so they cannot be both. There cannot be something. They cannot be simultaneously non-zero, because so uniqueness of B up to scalars implies that either B is equal to B symmetric or is equal to B alternating. So in other words, B has to be either B symmetric or B alternating. It cannot have a piece in one and a piece in another. So is that clear? Because each one of its components is G invariant, and what we just argued before is that there's only one sort of line of invariant bilinear forms. So here we have exactly this dichotomy. Well, I'm erasing it now, but I can add to the summary that if we start with a V irreducible with real value characters, then we get a bilinear non-degenerate. That follows, but it's not quite what I care about at the moment. Bilinear non-degenerate, which is either symmetric or alternating. And that is exactly the dichotomy that we're after. But we're now going to show that if the B that is completely unique up to scalars associated to the situation, if it's symmetric, then the representation is real. And if it's not, then it is not. Okay, so in fact, if it's not real, what happens is that the vector space, which is underlying our action of the group, is not only a vector space over C, but it's actually a module for the Hamilton quaternion. So in fact, such representations are called quaternionic. So this will exactly break up into two cases: symmetric bilinear form B, and this corresponds to real representation or quaternionic. So the representations from the point of view of the real numbers are going to come in three flavors. Either you are a complex representation, in other words, the character has some complex values, or your character has real values, and then you have two options. You either are definable over R, or you are quaternionic. Okay, this is for an irreducible representation. If you have a sum of representations, some can be real, some can be complex, some can be quaternionic, and you're not going to be able to tell just from the character immediately.
Sorry, but what's quaternionic about?
We'll see. We'll see that the vector space in question also is a complex vector space by definition, but it will also have an action of J, and will become a module for the quaternionic algebra. That's what I mean by quaternionic. Okay, so let's see how this is done. So let me summarize the story this way. We can argue as follows: if we define V prime as V where U and V are switched, this is another bilinear form that is fixed by the group. So it has to be the same as B up to scalars. Let's say a scalar epsilon, and by non-degenerate, you'll see that epsilon has to be plus or minus 1. So if epsilon is plus 1, we have a real representation. So epsilon here is a way to capture these two situations, symmetric or alternating. Okay, so let's now see how we can use this B to decide this issue of definable over R or not. So now let's backtrack and go back to the case of just any representation. then we did this a while back, but by averaging, we have shown that there exists a Hermitian non-degenerate form on B, which is G stable. Okay. Now, if V is irreducible, regardless of the character values, the same argument that we just did for B, let's call this thing H, okay, form H on B. H is unique up to scalars. Just the same argument as Schur's lemma. So now we have, on one hand, a Hermitian form H and a bilinear form B. They're both unique up to scalars. Now, B, well, I called it phi before, but I'm using notation a little bit, and determines an isomorphism from B to B dual, and H, similarly, will define an isomorphism from B dual to B. So, what this means is that, again, we have, by B and H, we have a map from V to V that is, well, let me be careful. Because they're non-degenerate, if I have two vectors u and v in my space, actually let me call them v and w. So if we think of this as a linear map, so let me put it this way. So fix a vector in V, then the map where you compute B of V comma anything, that's a map on the vector space V, is a linear map. Yeah? And since it's a linear map, and H is non-degenerate, there's some vector, which I'll call psi of V, that produces that linear map by pairing it via H. Yeah? And it's a unique vector because H is non-degenerate. The existence and uniqueness is because of being non-degenerate. And so what properties this map psi has goes from V to V and is additive. So if I take the sum of V1 and V2, psi of V1 plus V2 would be psi of V1 plus psi of V2. Is G invariant, because everything here is in G invariant. What is not quite true is that this is linear. In fact, it's antilinear. In the following sense, if we compute lambda of b v(w), this is b of lambda v(w). B is just bilinear. There's no mention of complex conjugations about b. This is, by definition of psi, h of psi lambda v w. On the other hand, if we look at the left-hand side, this is equal to lambda h of psi v w. Okay? And this is true for every w. Therefore, we must have the following. So this is true for all w. Hence, we must have the following. Let me do one more thing. H, the lambda, I can put it inside, but then it has to be conjugate. So psi of lambda v is lambda bar psi of v. So this map is not linear, but something we can call antilinear. And this is G invariant, as I said. Let's just see that. B of G U V is the same as B U G V, because B is G linear, rather G inverse. So this is the same by construction of H psi of U G inverse of V. Now H is G linear, so this is H of G psi of U V. On the other hand, this is H of psi of G U comma V, and this is true for every V, so that means that G psi of U is psi of G. So what we have then is a isomorphism, so it's a bijection which is additive, G invariant, and antilinear in this sense. Okay. So this guy psi will play the role of J in the quaternionic world, because see what happens when we square it. If you square psi, so you go, so psi goes from V to V, it makes sense to talk about psi squared, in other words, psi composed with psi. This also goes from V to V. But now psi squared is linear, because if we compute psi squared of lambda V, this is psi of lambda V. which is psi of lambda bar, psi of v, which is lambda psi of v. So psi squared is linear and G stable. This psi is stable. So what can we say about psi squared? I guess we lost it along the way, but we have psi v is irreducible. Yeah.
Scalar of.
So psi squared is an isomorphism from v to v, which is G stable. So psi squared is some scalar, again by Schur's lemma. So now let's see what we can say about this scalar. So H of psi u of v is v of u v by construction, but v is epsilon of v u. Epsilon is plus or minus 1. So this is epsilon of h psi of v u. And h is Hermitian, so this is the same as h of u psi of v conjugate. Okay, so now if we apply psi again, we'll find that h squared of u, phi squared of u, v is the same as u h u psi squared of v. We'll do this again. There'll be two conjugates in epsilon squared. Epsilon squared is 1. Now, this psi square of u is h of lambda u, which comes out as lambda bar. And on the other hand, this is lambda of v, which comes out as lambda h of u of v. So that means that this is true for any h, any u and v. That means that lambda has to be equal to lambda bar. In other words, lambda is real. So lambda here by Schur's lambda is non-zero because we have psi as an isomorphism, but it's bijective. So I want to now claim that lambda is exactly equal to epsilon. So let's see, or rather the sign of lambda is epsilon, to be precise. So let's compute h of psi of u, psi of v, according to this calculation here. If I replace v by psi of v, I'm going to get that this is epsilon of h of u psi square of v, all conjugate. Psi square of v is lambda v, which comes out of h as lambda, and because it's real, it's not affected by conjugation. actually I want to take this to be U. HUU is a real number. So I don't need the conjugation. And both of these quantities, h of both sides, they are both positive. If I take u a vector, a non-zero vector, h is a non-degenerate inner product. So that means that epsilon times lambda has to be positive. And so sine of lambda is equal to epsilon. Okay, so we have this real number lambda, which has the same sign as epsilon. And we can scale everything by lambda without changing things. So I can scale by absolute value of lambda to 1/2 or minus 1/2, so that psi squared is equal to epsilon. Yeah, can divide my psi by this quantity, which is a positive real number. Nothing of what we did will change. And now I can go back and say, okay, my psi, in fact, I could say that has the square equal to epsilon. It used to be lambda, but now I scaled it by the absolute value. And so what remains is the sign, but the sign is epsilon. Yeah. Okay, so this is, now we're ready to see a connection between epsilon and this question of what the representations being real or not. So suppose that epsilon is +1. Then we have this vector space V, and epsilon is 1, and we have a G linear map psi, whose square is the identity.
Sorry, it's anti-linear.
Yeah, anti-linear, thank you. Yeah, but is a map we can look at subspaces where psi acts as +1 and -1. So let me write this down. So let's think for a second the following thing. So think of V as a real vector space. It is a complex vector space, but you can think that we have a double dimension real vector space. Okay? So as a real vector space, psi is linear. Yeah? So psi is linear. Because if the real scalars come out just outside the same, only if it's a complex scalar, then it comes out conjugate. All right. So, and it's a linear map over R whose square is the identity. So it will have as eigenspace where it acts with +1 and an eigenspace where it acts as -1. These are dV plus and dV minus. Now, psi is G linear, and so these V plus and V minus are G stable. because psi commutes with the action of G. On the other hand, now what we think of is that we have a real vector space V, which has a map, which is multiplication by I. Because we know it's a complex vector space, so there is, and we know what a multiplication by I is. Is a map from V to V, but that map is R linear. So multiplication by I in V viewed as a vector space over R is R linear, and because we have a representation, is also G stable. And if we look at what happens when we compare it with psi, if I take psi of a vector u and I multiply by I, then we know that this is antilinear, so this is minus I times phi of u. Which means that if the vector u, so maybe here, if the vector u was in the plus space of psi, then I of u will be in the minus space. So I takes the plus space to the minus space. And similarly, I takes the minus space to the plus space. So I exchanges the V plus and the V minus. So one way to say this is that V is then V plus direct sum I times V plus. Or when it's the same, V plus tensor with C. So V plus is a G stable subspace of V. It's a real subspace. And to find the whole of V, you just have to double it up and multiply by I, which is exactly the effect of tensoring with C. So, in other words, V is real. Okay?
So why V is real?
Because it's equal to V plus tensor C. This is a G representation, and the V that we have is obtained by tensoring this real representation with C. Right? Tensor with C has this effect. This has 1 and I, so what you're going to have is vectors of the form V plus tensor 1 and V plus tensor I. So if I look at all the things that have a tensor with 1, they'll correspond to this term, and the ones with I corresponding to this term.
Here we are tensoring over R, right?
Over R.
Yes.
Yeah, it's a little bit confusing, this business between R and C. Hopefully I said all the things that are needed to understand it. You should meditate a bit. Now, so what we have just shown is that it's this sign epsilon that we had, which, remind you, means that this bilinear form that is G invariant is actually symmetric. Then we can see that the representation is real. And conversely, if the representation is real, then you can find a symmetric non-degenerate form that is fixed by the group, just by using the averaging technique. And so, since you produce a symmetric form fixed by the group, the epsilon is +1. So, not writing it down, but I'll write the conclusion. We have finally a criterion to decide whether the representations are real or not. So V is real. So here V is irreducible, and the character values are real. It's real if and only if epsilon is +1, which means, i.e., we have a G-stable, symmetric, bilinear pairing. Okay, now what happens if epsilon is -1? Well, now we have a map psi whose squared is minus the identity, and psi, the same thing applies here. Psi of I of u is minus I psi of u. So I times psi is equal to minus I times psi. So if we think of multiplication by I as R linear, psi as R linear, we have two maps, I and psi, which are R linear, commute with the action of G, and they anti-commute. So what it says is that V is a H module via I and psi.
I think there is a typo. Not should be minus psi I.
Yes, thank you. Yeah, so here, if I first multiply by I get minus if I multiply by I afterwards. Yeah. So this is the commutation relation exactly for the quaternion algebra. Psi squared is -1 and anti-commutes with I. So this real vector space is in fact a module for the quaternion algebra. So it has not only an extra linear map I, but it also has an extra map that is like J. And and then what it has is a fixed symmetric form, a bilinear form which is alternating. So the epsilon is -1. So this is why I was saying before, such representations are called quaternionic. Okay, so now all very good, but how do we tell if we are in one case or the other case? How do we get our hands on this epsilon? So epsilon has to do with what is the nature of the bilinear form that is fixed by the group. So let's say chi of V is equal to chi of V dual. So V is irreducible. So this means that chi has real values. We have to distinguish two possibilities. How do we do that? Now, I'll use V and V dual are isomorphic. So if we have, so let's try to figure out when do we have a skew symmetric form. I should put V dual, but this is isomorphic to V. So if we find such a non-zero B in here, then we will have a quaternionic. So this would be, so B is non-zero, In here, this is if and only if epsilon is -1. And how do we do this? This is a G representation, and B is a G stable bilinear form. So what we must have is that the dimension of the things that are fixed by G in this wedge 2 of V must be positive dimension, but we know that if it's positive, it has to be dimension 1 by Schur's lemma. Okay, but now this is something we can compute because the dimension is exactly the inner product of the character of wedge 2 with the trivial character. Okay? Now, and this, we already computed the character of wedge 2, and this, in a sense, is the main reason why we worked on these wedges, wedge 2 in particular. And if you recall, the formula was that you compute chi v of G squared, subtract chi of v G squared. And here's we can see how, as we were saying before, if you want to know the character of wedge 2 of V, it's not enough to know just the character values of V. You also need to know what happens with squaring in the group. And that's exactly what is going to make the difference between the quaternion and the dihedral group. The squaring map in one group is different from the squaring map in the other group. Okay, but the character values don't detect that. The values are the same, but the way the squaring works is different. So we want this to be equal to 1. So we're looking for when is this sum equal to 1. Now, V is irreducible by assumption, and is also, by assumption, has real values, a character of real values. So this sum, on the other hand, is the same as the sum with the conjugate. Forget where we put the conjugate, maybe here. Yeah? Because the conjugate is the same as itself, because the thing is real. And this is the inner product of V with V, which is equal to 1. Because it's irreducible. So this sum here decomposes into two sums. One of the terms is equal to 1. Therefore, we see that epsilon is -1 if and only if this sum is equal to 1, is equal to -1. Well, so let me put it as follows. I guess maybe we now state it as a theorem. V is irreducible. Chi of V is real. Then what we have is that the epsilon that we were after is actually equal to this sum. And so if you compute the sum, you will find three possibilities. So in other words, this sum is equal to 1 minus 1. So in general, the sum is equal to 1 if V is real. is equal to -1 if V is quaternionic. And if you compute the sum when the values of the character are not real, you'll find, in fact, that the sum is 0. So this sum completely breaks up, separates all three cases. And this sum here is called the Schur indicator. So we've done what we wanted. We have a reasonably straightforward way to compute whether a representation, an irreducible representation, is real, quaternionic, or complex. And you see that it doesn't depend just on the character values, it depends on the character values and what is the map of squaring in the group, which is something you cannot read off from the table. Yeah. And maybe I'll add it to the homework problem. If you compare the squaring map in the quaternion group versus the dihedral group, as I was saying, you'll find that it does different things. In fact, in the quaternion group, every element other than the identity and -1 plus and -1, all other elements have square -1. Whereas in the dihedral group, some have square equal to 1 and some have square -1, or whatever the element, non-trivial element of the center. So that means that is exactly what will make the sum different if you do it for the two-dimensional representation of D4 or of Q8. Okay? All right, so we'll continue on Wednesday.